Hi and welcome to this section where we are going to look at linear independence. Okay, now for a given set of vectors S, okay, given v1, v2, v3 and so on up to vn, there may or may not exist dependence relations, in the sense that it may be possible to express one vector as a linear combination of the others. For example, if we had this vector S consisting of just these vectors here, 1, -1, 2, and 3, 0, 1, and 9, -3, 4. Okay, then perhaps I hope you are able to see that if this is maybe v1, v2 and v3, perhaps you should be able to see that we can write v3 as linear combination of v1 and v2 with coefficient 2 and coefficient 3. Okay, in other words, v3 is 3 times v1 plus twice v2. Okay, and then we can write this and then say that 3v1 plus 2v2 minus v3 equals to 0. Okay, in other words, so we have some kind of dependence. That this vector v3 depends on v1 and v2. Okay, it can be written as a linear combination of this v1 and v2. What if we look at another example of, let's say we have these vectors here, b, these unit vectors, okay, 1 0 0, these unit vectors in R3, 0 1 0 and 0 0 1. Well, you can see that however much you try, you won't be able to find any kind of relationship with these vectors here, v1, v2 or v3. You can never write v1 in terms of v2 and v3, neither can you write v2 in terms of the other or v3 in terms of v1 or v2. Okay, so here we see that you have no kind of dependency, while here we have some dependence. Okay, so now that brings us to what we want to look at today, which is about linear independence and linear dependence or linear independence. Okay, so it would be good for us to note, or we can note, that for such a case, okay, if we were to write it in the general form, maybe alpha 1 v2 plus alpha 2 v2 plus and so on alpha n vn. Okay, in other words, we can, if we are to solve this homogeneous system here, we can be able to find values of alpha 1, alpha 2 up to alpha n, not all 0. Okay, not all 0, not that, not maybe 1 or 2, maybe 0, but we are going to say that not all what is 0. Okay, in this case where we have dependency, it is able to compute for the coefficients here, the ones we are calling alphas. Whereas for this kind here where we have no dependency, in other words, no dependence, the only solution here we are going to get is, since there is no dependence, that means all the alphas are 0. So we have said that for dependence, okay, we are able to find at least some kind of alphas which are not all 0, i.e. not trivial. Remember, we said that for homogeneous system, if we find a trivial solution, it means that all the alpha i's are what? Are 0. So we are saying that if we have some kind of dependence, then we are sure that we can get any other solution apart from the trivial solution. However, if you can clearly see that if there is no dependence here, if we try to solve for this, we won't find any of these alphas there. They will not be what? Existing. They won't be existing there. Okay, and we shall see. Okay, let us maybe look at an example here. So maybe a definition here about now what we call linear independence. So we are going to say that the set S of vectors given as v1, v2, and so on up to vn is said to be a linearly independent set, linearly independent, whenever the only solution for this combination here, alpha 1 v1, alpha 2 v2, and so on up to alpha n vn equals to 0 is, okay, the trivial solution, i.e. alpha 1 equals to alpha 2 equals and so on up to alpha n is equals to 0. For this case here, where we said we have no dependence, if we try to solve this equation here, for this case where we have no dependence, then we cannot find these alpha 1s, alpha 2, and alpha 3s. Therefore, they will all be 0 actually. The only solution that we are going to have is 0. So we shall have to end up with, 0 equals to 0. But if we compute it for if there is some kind of dependence here, then we should be able to get some other solution apart from the trivial solution. Okay, so whenever there is a non-trivial solution, so just the opposite, that whenever there is a non-trivial solution, i.e. not all the alpha are zeros, okay, then we say that the source set is linearly dependent. In other words, in summary, if we have a set S of vectors v1 up to vn, okay, if we want to check whether the set is linearly independent or linearly dependent, we simply write down this homogeneous system and then we try to solve it. So if we find that alpha I is equals to 0, i.e. the only solution is a trivial solution, then in such a case our set is linearly independent. However, if we find that not all, any one is not 0, then we have linear dependence. Let us look at a quick example here. Quick example would be that we want to find out whether the set S consisting of these vectors here 1 2 1 1 0 2 and 5 6 7 is linearly independent or not. So we said we are simply going to solve alpha 1 v1, alpha 2 v2, alpha 3 v3, and then we solve for the homogeneous system. Okay, so maybe we can write this as 1 2 1 1 0 2 5 6 7, and then we have alpha 1, alpha 2, alpha 3, and then we have 0 0 0. Okay, so how can we try to solve this? We try to solve this by reducing this. I would say that we would augment, but there is no reason to augment because the right hand side is 0. Okay, we are not going to change anything. So let us just reduce this one here using to echelon form, row echelon form. So we try to make this 0, so R1 went to R1, then minus 2 row 1 plus row 2, we put the result in row 2. So multiply by negative 2 and add, we get 0. Multiply by negative 2 and add, we get negative 2. Multiply by negative 2, that is negative 10, and add 6, we have negative 4. Multiply by Okay, so here we have minus row 1 plus row 3. We put the result in row 3. Multiply by negative 1 and add, we have 0. Multiply by negative 1 and add 2, we have positive 1. Multiply by negative, that is negative 5, and add 7, we have 2. Okay, so we still reduce this further. Row 1 goes to row 1, and then maybe we can make this a positive by saying we multiply row 2 with a negative and we put the result in row 2. We are just multiplying it by a non-zero scalar, which is negative 1. So that means that it remains, this becomes a positive, and then by the way, we can even say by negative 1/2. We can multiply it by negative 1/2. So we multiply by negative 1/2, that becomes a 1, and that will become a 2. So this remains as it is, 1, 1, and 5. And now, okay, maybe we can say that row 3, we first leave it as it is. This is 0, 1, and 2. And then perhaps in the next step, we can say row 1, row 1, row 2, row 2, and then negative row 3 plus, negative row 2 plus row 3, and we put the result in row 3. So we have 1, 1, and 5. We have a 0, 1, and 2. Multiply by negative and add, we have a 0. Multiply by negative and add, we have a 0. Then multiply by negative and add 2, we have negative 3. So we realize that after reducing this matrix here to this echelon form, echelon form, we realize that we have the only solution we are going to get is a trivial solution. Why? Because we have reduced it, and we have 3 equations, and the unknowns are 3. In other words, you can just do back substitution here. You can actually see that alpha 3 is going to be 0, alpha 2 is going to be 0, and also alpha 1 will be 0. But you can just look here that the matrix here, okay, we don't have any case where we are going to get infinitely many solutions, if you remember the section on that. So in here we can actually see that the only plausible solution is the trivial solution, for which alphas are equals to 0. And in such a case, we say that if the only plausible solution is the trivial solution, then this set is linearly independent. Linearly independent. If we had seen otherwise, that we are capable of getting any other solution which is not the trivial solution, i.e. perhaps let us say, okay, this is, I want to leave it like that. If maybe this had reduced to 0, you realize that if we had found out that that reduced to 0, so we would have a case where we have just 1 equation and 2 equations and 3 unknowns. Then we would go into what we did last time of trying to find which is the leading variable, which one do we set, which is the free variable, which one do we set as a parameter to be written in terms of the other, and then we have infinitely many solutions. In such a case, we have a solution which is non-trivial, and therefore this set would be linearly dependent. However, since we have found out that the only plausible solution here is the trivial solution, therefore we can say that this set is linearly independent. So thank you. I hope you've been able to understand something. You can take some time and look through the video again in case you have not understood, or you can put your questions in the comment section. So thank you, and see you in the next video.